Problems involving friction can be particularly challenging to understand using the energy principle. Today we'll discuss a seemingly simple exercise that will tell us something surprising about energy transfer involving friction. Here's the situation. Imagine that you pull a block of mass m along a level surface with a rightward pulling force F of constant magnitude. The block moves at constant speed as the block undergoes a rightward displacement of magnitude d. Let's choose as our system the block and use the energy principle to tell us about the change in thermal energy, delta E thermal, of the block. We expect the block's temperature to increase, which means thermal energy increases, because as the block rubs against the level surface, friction acts to dissipate energy. Let's start by first applying the energy principle in a point-particle model, which means we focus only on the change in translational kinetic energy of the block, which is equal to the work done by all interactions of the surroundings, expressed as forces, acting on the block at its center of mass. There are three agents: U, applying the pulling force, the earth, applying a weight force, and the surface, applying a contact force, which we express in terms of a part perpendicular to the surface as a normal force and a parallel part, which is the friction. Now, since both the weight and the normal force are perpendicular to the displacement, these forces do no work. So we focus on the work done by the pulling force, big F, and the friction, little f. We know that the block is moving at constant speed, so the change in translational kinetic energy, K trans final minus K trans initial, is 0. This means the total work in the point-particle model must also be 0. So if we expand the work done by the pulling force and the friction, both acting through the center of mass displacement, we see that this work is 0 only if the friction force is equal in magnitude to the pulling force. This all makes sense, and in fact, we could have arrived at the same conclusion by applying Newton's second law to this problem. It's a case of dynamic equilibrium. Now let's look at the full multiparticle situation. Now delta E, the change in the total system energy, must also include changes in internal energy, here the change in thermal energy, and the sum of all energy changes must equal the work done on the system, the block. Now, as we discussed, delta K trans is 0, so the total change in system energy is just equal to the change in thermal energy, delta E thermal. So to find this, we need to find the work, which again, we only have non-zero contributions coming from the pulling force and the friction. The work done by the pulling force in the multiparticle model is computed using the center of mass displacement. So that work is the same as in the point-particle model. So we know what that is. We still need to compute the work done by friction in the multiparticle case. Now, what is that? In particular, we know the friction force is constant and equal in magnitude to the pulling force, based on our results from the point-particle model. But what do we use for the displacement for the friction in the multiparticle situation? If we try using the center of mass displacement, we end up with a contradiction. The right-hand side of the energy principle would then be 0, suggesting delta E thermal is 0. This suggests that the block doesn't warm up as it rubs against the surface, but we know that's wrong from experience. We can simply rub our hands together and feel the increase in temperature as friction acts to dissipate energy. So the displacement through which the friction acts must be different from the center of mass displacement. But what is that displacement? To understand this, we need to visualize what happens at the microscopic scale at the interface between the block and the surface. At small scales, a typical solid interface is not perfectly smooth. In fact, there is a roughness that shows up as microscopic protrusions, sometimes called asperities, that stick out from both the block and the surface. It's these protrusions that actually make contact and support the block on the surface, and the rest of the interface is mostly a gap filled with air. Now let's picture what happens when, say, a protrusion from the block makes contact with a protrusion from the bottom surface as the block displaces to the right, relative to the surface. The protrusions would deform like this because of the friction force that acts at the tips of the protrusions. Now here's the key point. We see that if the block undergoes a displacement of magnitude d, the displacement of the protrusions at the location where friction acts, at the tips, has a smaller magnitude, say d sub f. Eventually the contact between these protrusions is broken. This breaking action results in the dissipation that increases thermal energy, and other protrusions will take over in making contact. However, in all cases, the overall effect is that the magnitude of the displacement associated with the friction force is smaller than the magnitude of the center of mass displacement d for this particular situation. So now we can return to our energy principle for the multiparticle system and use the fact that d sub f, the magnitude of the effective displacement for the friction force, is smaller than d, the magnitude of the center of mass displacement. We see that the overall work is now positive and equal to the change in thermal energy, which suggests that the thermal energy increases, which is in accord with what we know from common experience. Now let's push this a bit further and interpret what the energy principle is telling us here. We see that the work done by the pulling force is positive. This means the pulling force transfers energy into our block. Now, none of the transferred energy shows up as energy that affects the macroscopic motion. The block moves at constant speed. However, some of that transferred energy does show up in the system as internal energy, an increase in thermal energy. The block warms up, increases in temperature. The remainder of the energy transferred in by the pulling force is transferred out. That's the work done by the friction force, which we see is negative. Now, where does that energy go? That energy transferred out of our system of the block shows up as an increase in thermal energy of the surface. So, bottom line here, we find that in working this example, we have learned quite a bit about energy changes and energy transfer in this case, where the dissipative force of friction is at play.